In this section, we're going to introduce a few properties of the Mobius function mu and lambda. And these properties will be very useful in our proof of the Selberg's asymptotic formula. Some audience might be already familiar with these properties, and you can feel free to skip through this section of the video series. Now let's talk about the Mobius function mu. The Mobius function mu is defined as follows. First, mu of 1 is equal to 1. And second, mu of n is equal to 0 if n has a squared factor, and if n does not have a squared factor, meaning n is a product of distinct primes, say there are k distinct primes, then it is defined as -1 raised to power k. Or some people may prefer to write this as mu of n equal to -1 to the power k if n is equal to p1 times p2 all the way to pk, with p1 through pk distinct primes. And is equal to 1 if n is equal to 1, and 0 otherwise, in which case there's a non-trivial squared factor in n. And now let's talk about a few properties of the Mobius function. Again, we will use the same labeling as in Harday's book. This property says, if you sum up mu of d, where d is the divisor of the integer n, then the sum is equal to 1 if the positive integer n is equal to 1, and 0 if n is bigger than 1. And now let's prove this. The proof is done by using the prime decomposition together with the binomial formula. If n is equal to 1, the sum is really trivial. This is just a mu of 1. And now if n is bigger than 1, then we can write the prime decomposition for n. Say n is equal to the product of p1 to the a1, p2 to the a2, all the way to pk to the ak, with p1 through pk distinct. And now we can calculate this sum. The summation will become, to compute this, we're going to stratify this sum. First, we single out the case when d is equal to 1. And in the second stage, we're going to sum up all those d's, which is equal to 1 prime factor here, namely mu of p sub I, for p sub I equal to p1, p2, all the way to pk. And next, we're going to sum up all the mu of p sub I times p sub j for all distinct pi and pj here. And we keep going. The first guy, mu of 1, is equal to 1. And the second guy, by definition of the Mobius function, this guy is equal to -1. And in total, we have summed up k many -1s. So in the next stage, you get k. But there's a negative sign in front of it. And next, it will be k choose 2, because we are considering all possibilities because we are considering all choices of pi pj's among p1 through pk. So there will be k choose 2 cases. And this sum will be alternating. Next term will be k choose 3 with a -1 in the front, because it's a product of 3 things. And in general, for the rth term, we're going to get -1 to the rth power times k choose r. And the last term will be -1 to the k. But what is this? This is precisely equal to, by the binomial formula, 1 minus 1 raised to the power k, which is equal to 0. So here we have used the fact that n is bigger than 1. Otherwise, there's no prime factor in n, and this argument doesn't make sense. So there are indeed 2 cases when n is equal to 1, the sum is equal to 1. If n is bigger than 1, the sum is 0. Now, among all properties of Mobius function, the Mobius inversion formula is especially important. The Mobius inversion formula states as follows. Let f and g be 2 functions from the set of integers to R. This is called arithmetic functions. Now if g of n is equal to the summation of f d's for d ranges over all divisors of n, then f of n is equal to the summation of all mu of n divided by d times g of d for d divides n. And you can also write this so-called convolution in another way. By summing up all divisors d of mu of d times g of n divided by d. And you can easily see that these 2 sums are equal. And now let's prove this. We'll start from the right-hand side with this convolution. Now we plug this equation that g of n is equal to f of d, where d ranges over all divisors of n, into g of n divided by d. And you will become, now you are treating this n over d as a separate integer. So now we are considering all divisors of n divided by d of f of c, where c ranges over all divisors of n divided by d. And now we're going to merge these 2 iterated sums into one sum. These 2 sums together will give us the summation of mu d times f of c, where c times d divides it. So here we are considering all divisors c and d of n, and at the same time c times d is also a divisor of n. And we sum up mu of d times f of c over all such possibilities. let us rewrite this sum in a different form. Let us first, for each c divides n, we sum up all mu of these with d divides n over c. And then we sum up all of f of c times the sum, where c divides n. And you can think of this process as the finite Fubini theorem. But now, what is this part? What is this sum? By our previous theorem, this sum is equal to 1 if c is equal to n, and is equal to 0 if c is a divisor that is less than n, meaning n over c is at least 2. Therefore, the only term survives here is the term when c is equal to n, in which case you get just f of n. And hope this makes sense. And now we connect the Mobius function mu we just defined to lambda. Recall, the lambda is defined as log of p if n is a non-trivial power of p, and 0 otherwise. Remember, in particular, lambda of 1 is equal to 0. The first formula we're going to show about lambda is the following. We show that if you sum up lambda of d for d divides n, you will get precisely log of n. And you can easily imagine the reason we want to show this is that we want to connect this to the Mobius inversion formula. So how do we prove this? This is proved by combinatorics, namely by counting. Again, if n is equal to 1, then the statement is trivial, because lambda of 1 is 0 and log of 1 is also 0. Now if n is bigger than 1, then we use a prime decomposition again. In view of this prime decomposition, what is the summation on the left-hand side? The summation will become, first, by definition of lambda, the sum is precisely equal to the summation of log of p, where there's some power of p divides n. More precisely, in view of this prime decomposition, this sum is actually equal to, now for each prime factor of n, we count the multiplicity of that prime factor in n. For example, the multiplicity of p1 is r1, the multiplicity of pk is rk. So in total, we are summing up r1 times log of p1 plus rk times log of pk. So for this equality, you look at, for each piece of I, how many terms are there so that the piece of I raised to the power m divides n. There will be precisely r sub I terms. So writing it more explicitly, p sub I divides n, p sub I squared divides n, all the way to p sub I Ri divides n. That is why in front of log of p sub I, you should get r sub I. So if you understand this, you will see immediately this is precisely equal to log of n by the product rule of log functions. So we are done with this proof. And as an immediate corollary to this, here we are still using the same labeling with the hardest book. Although this is a 295 and this 296. This is a corollary to 296. As a corollary, let's see why this equality is true. This is true simply because of the Mobius inversion formula, which is the theorem 266, together with 296. Because the log function here plays exactly the same role with the function g here. Log of n is equal to summation of lambda of d, where d divides n, is same as the condition that g of n is equal to summation of f of d, where d divides n. So, by the Mobius inversion formula, you should get f of n, which corresponds to lambda of n here, the summation of mu of n divided by d times log of d, for d divides n. So this is very straightforward from Mobius inversion formula together with this theorem. At the end of this section, let us prove another interesting theorem that looks pretty much similar to this one. We'll show that lambda of n is also equal to the negative summation of mu of d times log of d for d divides n. So how to prove this? This equation basically had nothing to do with the Mobius inversion formula. Instead, we're going to just prove this with combinatorics. First, if n is equal to 1, then you still get the trivial equality, because left hand side will be 0 and right hand side will also be 0. If n is a single power of p for some prime p, then the left hand side is equal to log of p, and the right hand side will be equal to, now you consider all divisors to this power p to the mth power. Because mu of d is 0 if d contains a square. So there are only two cases where mu of d is not equal to 0. One case is when d is equal to 1, and the other case is when d is equal to p. But as you know, log of 1 is equal to 0. So there's only one non-zero term in this sum, which is mu of p times log of p. But what is mu of p? Mu of p, because this is a product of only one prime, so it will be negative 1, and negative 1 is equal to positive 1, so you can get log of p, which is equal to the left hand side. So this verifies the case when n equals to the power of p. Now, if n is not equal to 1 and n is not equal to a power of p, which means by the prime decomposition, n is equal to p1 to the r1, p2 to the r2, pk to the rk, for k at least 2. Then again, let us consider the sum on the right hand side. Let us ignore that negative sign in the front, because in this case, we're going to show this sum is equal to 0. Because when n is not the power of p, lambda of n must be 0. So we are supposed to show this is equal to 0. And the trick here is that we are only going to count those non-zero terms in this sum. Since there are a lot of possibilities, we're going to only focus on the following case. First, we only consider the non-zero terms. This already means we're only going to consider the terms where d is square free. And second, you can see we can rewrite the sum as the summation for I equal to 1 to k of some coefficient lambda sub I times log of pi. Because each d must be the product of some powers of p sub i's. And when you break down that product, you will see the sum will eventually become the summation like this. For each log of p sub I, there's a complicated coefficient in front of it. And our goal is to show that each sub lambda I is equal to 0. And thus finishes the proof. So now how do we show each lambda sub I is equal to 0? In fact, we're going to explicitly compute these lambda sub i's by counting. Lambda sub I claim, is equal to, first, if you look at the case when d is precisely equal to this p sub I, then the coefficient in front of that is just mu of p sub I. If you look at the case when d is a product of p sub I with some p sub j, then in that case, the coefficient in front of it will be the summation for all j not equal to I of mu of p sub I times p sub j. And now the general term looks like mu of p sub I, p sub I1 through p sub IL with I sub 1 through S sub L all distinct, and they are contained in the set from 1 through k with I omitted. So summing up all such possibilities, and that will be the coefficient in front of log of p sub I, where d is the product of L plus 1 things. Hope at this point you can understand what's going on here. Once you understand this part, the rest should be easy, because you can explicitly compute each of those sums. The first one is just -1, and the second one is k minus 1 choose 1. The third one is minus k minus 1 choose 2. For the general term here, it will be 91 raised to the power L plus 1 times k minus 1 choose L. And now if you pull out this -1 to the front, you will get, now let me rewrite this. Does this look familiar to you? It should be, because this is precisely the binomial expansion of -1 minus 1 raised to the power k minus 1. Because k here we assume is at least 2, so this must be always equal to 0, which is also equal to lambda of n, because n is not a powerful prime. It's a product of many things. So lambda of n is equal to 0. And that finishes the proof. And starting from the next section of the video series, we'll start talking about the famous Selberg's asymptotic formula.